Recording in progress.
Yes, so once again, welcome to the lecture on Biocatalyst enzyme technology. Yeah, I received several questions in view of the examination, how the examination looks like. And in the end, the examination will be running for written examination in presence at the 2HH, and it will be running for 90 minutes at the given location and time that is already posted. And you just need to bring your pen. You don't need to calculate anything where you need a calculator or anything. So just your pen, paper will be there. And the examination is set out of two parts. The first part, and it's calculated in that sense that for each part you would approximately need 45 minutes, so that in 90 minutes, so half time, you have both lectures being considered. And so the first part will be this lecture, Biocatalyst enzyme technology, and the second part will be technical biocatalysis lecture. And the questions that you get there are the same one. No, they are not the identical one, but in the style of questions that we discussed in the auditorium or the online. So like on the blackboard, for example, assign a chirality to R or S, or how can you synthesize this compound? We did this on the blackboard twice, also making use of the knowledge that you have learned in lecture. You don't need to know specific names of individual strains of microorganisms or individual detailed information about the industrial process, but you need to know, and that's true for both lectures that are being part of the examination, you need to know the principles. The principles we've talked about in the lecture. For example, in technical biocatalysis, that you know how can I transform from a plug flow reactor into a CSTR performance. And then you should be triggered, okay, I need to switch over to circulation reactor and I have a specific ratio of the residence time and circulation pump being larger than 20. So these principles you should be aware of and should be able to apply to different challenges or cofactor regeneration. Yeah, so for NADH, so you should be triggered. There was something like thermodynamic limitation. There are two principal systems. What could be the possible systems to be applied? What are advantages, disadvantages? What system might run nicely in organic phase? What might rather require an aqueous phase? So all these points that we discussed on the whiteboard, but if you were not able to take part in the in the lecture during the semester, will also be covered in the videos that you can see, because this I always discuss every semester normally. So I was contacted by two students who arrived just before Christmas because of the pandemic situation here in Hamburg, and from that time point could only take part in the lectures, which were carried out at the time still in presence in the auditorium. So it's no problem. So for the examination, all relevant information you can also find in the videos beside transparencies. Are there any questions? Then please either write into the chat, or you're also more than welcome to open up your microphone and just to ask a question.
I have a question. Are you allowed to bring notes? And are you allowed to bring notes on a digital device, like, for example, a form of tablet or a computer?
No, there are no notes allowed. So in the end, you should learn the topics, the principles, like what I mentioned just before. And since we are more on a principle level, so there will be no specific, let's say, formula. Okay, you should know Miguel-Menten, and you should know that maybe a double substrate Miguel-Menten, you should be able to formulate. You might need to know white sides, so Ki over Km, what those ratios might mean, so this stuff. But you don't need to have a huge collection of any formulas you might need to know, or specific chemical structures which you can only make use of with your notes. Is that okay, or?
Yes, that is okay.
Yeah, any further questions to the examinations? Okay, I don't see any further. So I will ask the same tomorrow morning again in the technical biocatalysis lecture, so feel free to ask, because we just have 2 lectures left over, and we will use these 2 lectures for practicing a bit application of these principles. But yeah, feel free also to ask, and also if you're starting learning and you find out, oh, this I didn't understand at all, so don't be shy to ask here openly. I'm happy to explain it to you, because you could for sure be sure that if you haven't understood it, there might be at least a further person who haven't understood it, and so it might be good to explain it anyhow again. Okay, I don't see any further questions or comments. Then I
yeah. Oh, sorry. I remember one last thing. Is of course you will go through some examples in class, but are we able to see some of the previous exam sets maybe, so we have a idea of what to expect?
Yeah, we don't have a collection of former exams that we distribute, but as said, it's the same style. It's identical to the problems we're discussing in both lectures. Yeah. So what we're discussing on the whiteboard or here with the iPad, what I'm writing handwritten, those are typical examples, questions that I'm posing, or that we are posing also there. And maybe Fernando can comment this, because Fernando also is my substitute sometimes. He did study the same course than you did. He's now a PhD student in my group, in my institute. And yeah, maybe you can comment how it was from the time you were joining in here as auditorium.
Yeah, sure thing. Yeah, the exam, as Professor Lisa said, is mostly about the concepts rather than numerical or calculation exercises. You should understand the theory and the principles behind all of the topics covered in the module. It is good if you also can know what happens in terms of graphs. Graphs are very, very useful, and so I would recommend you to study how to draw different plots, whether it is EE versus concentration or conversion, sorry. Yeah. Or how PFR compares to CSTR, so on. So that would be my advice.
Yeah, thank you. So I think the point is, if you really were thinking along during the lectures, and take a look at the videos where you see the same discussion as with lecture hall. It was taped during the pandemic situation a year ago before, but same examples and so in a comprehensive manner are discussed. And so you should be able, the questions that I pose in the lecture, to answer for yourself. And if you cannot answer them for yourself, so you're somewhere trapped, then talk to colleagues, or use the time this week or next week in any of the lectures to ask a question. There is a further question from Sarah.
Hello, sorry. I would like to ask about the organic chemistry parts. For instance, do we have to name the chains or the reactions, what did react with what compound, or some stuff like this? I mean,
yeah, you don't have to name them, but you should be able to draw them. Yeah. And so, for example, we will also practice this today. So we have one example. We're going through in detail on the whiteboard or iPad here. I'm drawing and we're discussing. But let's say your chemical structure will be given like what we had before an architect, for example, and then you should be able for sure to draw the enzymatic reactions, not the mechanism, but what are the starting materials, what are the products, what is the enzyme that I can use to apply to generate these products. To answer the question, would that be something more I would run in an aqueous environment, or would I need to use an organic environment, or does it not matter in this case? So like what we discussed in the classroom.
So basically knowing the organic group would be enough for the reaction, yeah?
Yeah, right. So you don't need to transfer a name to chemical structure, and you don't need to transfer a chemical drawn structure to a chemical name. Yeah.
Yeah.
But you will always get either you will get a reaction where there are questions to, or you get a structure as a product or starting material where there will be a question, how could it being reacted with different enzymes, or how could this be synthesized? Or it might be that you get any, serial or parallel reaction that you should judge how you can select for a target or so. So like what we discussed in the lecture.
Thank you very much.
So the transparencies are, let's say, the know-how, the principles that you need to know, and the examination will at the same time point, like what we have done on the whiteboard or here on the iPad that I'm drawing. Okay. But we will do also one detailed example today, so you will see. Further questions or comments?
Professor,
Yeah.
like in the case of decarboxylases, we have different names for the enzymes, like pyruvate decarboxylase, something like that. So can we just write decarboxylase, or do we have to write the entire name?
Well, it's always good if you know all the detailed name, like pyruvate, or there's also benzyl formate decarboxylase, but decarboxylase will also do. But it's better if you learn the details, because later on in your business environment, when you finalize the QHH, it would be good if you know a little more details. But this I will repeat in a moment. So we're starting up with a repetition from last time, and then we'll do an example in detail. Further questions or comments? Okay, I don't see any now. Yeah, then I will switch over to the transparencies. So this is from last time, where Fernando substituted me. So thank you again to Fernando, once again. Chat box. Okay, there, I just see there. We still have a question in the chat I read out. I would like to know if there's any particular topic you find difficult for students along years. Fernando already has answered, sorry. It changes depending on the background of the student, and from year to year, there's no single topic that's particularly difficult. You have to identify for yourself that we don't feel so confident. That would be my advice. So second question I will answer in a moment. What I can add to this, so just over the years where students feel challenged, for sure is kinetic resolution. Yeah, what we discussed in detail. Often students have problem EE, conversion, inhibition. So this topic, and if you feel yourself unsafe, I'm for sure, I know there are a lot of people in the classroom who have understood this just by the Mentimeter questions that there were. So talk to your colleagues, to your co-students, or feel free to ask if you've learned next week question what there will be, which I am happy to answer them. But this is one topic, and some, depending on your background, some also have challenges between plug flow reactor, continuous to tank reactor, and patch. I often observe that is what Fernando already pointed out. So you should be able that I poke you during the night, and you know what are the advantages, disadvantages of a plug flow reactor in contrast to the profile of a CSTR, continuous to tank reactor. And these are the principles that in the end, later on in industry you will need, because you're sitting on this side of the desk, your co-worker will come up to you present your data, and then you have to judge it. Therefore, it's so important to know these principles to judge. Then there's a question from Tobias. Is there also an exam in German? No, there's none. So it's an English module, the International Master Study course. We are offering it to HH, and so also the examination is in English. From my now the question is, how do you answer? And from my point, is it okay? So normally would be to have an English answer, also in the examination. However, it's okay if you do the answer in German, but then make sure that you use the right terms also in German. What we did not always introduce in the lecture, because the lecture by the study course being purely in English. But for example, plug flow reactor in German is der Strömungsrohrreaktor, or CSDR is der kontinuierlich betriebene Rührkesselreaktor. So make sure that you use the right terms in German, but questions will be in English. Dominant language and answering should be English. Please, the only thing is, don't make a mix-up. Yeah? So if you decide for yourself answering German, that's fine, but then do it on total and not a mix, because that then have to judge sometimes what the answers. Any further questions though? Okay, I don't see any. Yeah, then we will start up and continue. We will start up with a repetition. And last times, no? Chat over here. So last time you did a quick path through ligases, isomerases, and ligases, and I would like quickly to repeat this for you, and then I will add one point because of time Fernando couldn't address last time. Yeah, ligases enzyme class 4, they are being used in cleavage, so this could be a carbon-oxygen, carbon-nitrogen bond, or some other bonds, often leaving unsaturated products with double bonds. And typical for ligases, it's always a 2-to-1, so two starting materials being combined to one product, or one starting material being split in two products. In contrast to when we had oxidortases, transaminases, hydrolases, we always have 2-to-2. So we have two starting materials. Oxidotases was an alcohol, for example, or ketone with a cofactor generating a cofactor that was changed in the product. On transaminases, we have transferases, example, transaminases. We might have an amine donor, we have an acceptor, and then on the product side, we have the amine as product, and then we have the second co-product. Or in hydrolases, remember, we have, for example, hydrolysis, where we have water with the ester reacting, and we're generating alcohol and acid in consequence. So at the end of the day, until enzyme class 4, we always have 2-to-2, and ligases, first time we have 2-to-1 or 1-to-2, depending on the direction of reaction. Yeah, and then here come into play also our chirality knowledge that we had in the chirality lecture, because if we have a 2-to-1 reaction, we're looking from the left side, so here we have a double bond, we're adding a compound that is being added up here, so it's HX, so X is added and the H is added, so it's 1-2 starting materials. And wait one moment, pointer. So it's 1 and 2 starting material generating one product. And now the special thing is, so far in 1-3, we most often had chiral centers, tetraeder, so at the carbon, for example, for residues. This we do not have here. So in this case, what is shown here, we have a double bond. So we have only 1, 2, 3 residues for this carbon here. And therefore, it's just 3 residues, it's in a plane. That's what's shown here. And now if you remember the chirality lecture, you could have an attack from the re or C phase side. And if you remember, that's the transparency from the chirality lecture. We're applying the Kahn ingot product rules, looking from the top or from the bottom. So we will have a turning point, left or right point, which will be S or R, pro S, pro R, or V and C phase. So just to repeat this here, on the C side, we're looking at this carbon with 1, 2, 3 residues, and hydrogen is the one with the lowest, you already know. Then the second one is a carbon, because heteroatoms are counting higher, so it will be 1, 2, 3. And in consequence, we can determine a direction of travel. Yeah, and the examples in terms of enzymes that we have was fumarase and aspartase, both large-scale being applied processes. And in case of the fumarase, we're adding water to double bond, what you see here, and you're generating a chiral alcohol. And depending on the type of fumarase or what strain it comes from, the product will be either R or S selective, depending if the water is added from the top or from the bottom, so to say, because this is a plane. Yeah, and if so fumarase adds water, and reaction mechanism you don't need to know. It's nice to understand, but you don't need to know for the examination. And if you're adding instead of water ammonia, then we're producing not like here the hydroxy acid, which is malic acid, starting up from fumaric acid, therefore fumarase, fumaric acid. Here we are producing as a product aspartic acid, namely the amino compound. So we're adding the amine to the double bond, and therefore this is named aspartic acid. And the nice thing is that in both cases we can yield up to 100% yield, because the water molecule or the amino molecule is totally with all atoms added to the starting material to generate this product. Both processes are scaled. The first one, the example, was from Amino GmbH, GmbH in Germany. This is the aspartase, an example from Japan. Mitsubishi is running it, for example, there, but there are many more out there. Yeah, and then this opened up thinking about decarboxylases. And as the name already says, decarboxylases are enzymes that split off carbon dioxide. So here's a 1 to 2 reaction. Beforehand, we had a 1, 2, 2 to 1 reaction. And now we're splitting something off. So it's a 1 to 2 reaction. And we're just splitting off carbon dioxide. And so that's the action of the decarboxylases. And one point that we discussed also with Fernando, or Fernando discussed with you, might be rather right, is a challenge that you're generating carbon dioxide. And carbon dioxide, right down here, occurs stoichiometrically. So we have 50 liters of carbon dioxide approximately per liter reaction mixture. If we apply, if we generate 2 molar of the aspartates. So in the first step, we're generating the aspartate with the aspartase. And then in the second step, we're splitting off this carbon dioxide. So it's a reaction sequence on scale in process with 2 enzymes in fixed bed reactors. And Fernando talked with you about unstable conversion. And we also had it in technical biocatalyst lecture already once, meaning if we're generating this carbon dioxide, and this carbon dioxide is degassing in this packed bed reactor, we're taking away liquid volume, because if it's degassing, we have gas volume. In consequence, if we're taking away liquid volume, then we have less reaction volume in this packed bed. And remember, residence time was defined as volume divided by flux. So meaning if we have the same residence time, the same flux, if we have the same flux through the reactor, because the pump generates a flux in liter per hour, but the volume is decreased, the liquid volume with our reactants, the residence time becomes shorter because it's volume divided by flux. And in consequence, we have less time for reaction and we will gain less conversion. And therefore, we have an unstable conversion until the point the gas bubbles are leaving the reactor. The gas volume can be filled with liquid volume again, and in consequence, residence times get longer. Solution to this challenge, that's a fundamental principle. What I meant, you need to know for the examination. What was the solution? You put what you have in your sparkling water bottle, we put on some overpressure. Also, the sparkling water bottle you're carrying at home has some pressure built up inside. And if you open up the water bottle, you release the pressure and it starts bubbling. And same principle here. So we have overpressure, slightly 0.1, 0.5 bar on the reactor, max 1 bar. And in consequence, the carbon dioxide that is formed because of the reaction is not degassed in here. So we maintain the liquid volume, it will be solubilized, and as soon as it exits the reactor up here, it will be degassing. And because there normally we still have a valve or something like this. And so that we have a constant reaction volume in the packed bed. Important principle being applied for several reactions. Yeah, then we were switching further on, still with amines, nitriles.
Excuse me, sir.
Yeah, sure.
I have one question. So, as we are talking about the aspartate beta decarboxylase, so we are splitting off the carbon dioxide, and this is our prime object. So, why we are putting more pressure to get it absorbed again?
Okay. Then we won't. I just need to open up my whiteboard. One moment. I'm just switching. Okay, now you should see my whiteboard. Let me explain it once again, okay?
Thank you.
So the situation is, we have a packed bed reactor, and in this packed bed reactor, we generate a flux to the pump, and this pump generates a flux V, okay? Now, out of this, in this reactor, we do have our particles with immobilized enzyme, and so on. Should be equally filled, yeah. And the room between, the room between these particles, that's the liquid volume, yeah, passing through the reactor, and maybe still in the pores of the particles. So this is the volume, the reaction volume. Now we have defined that the residence time is nothing more than the quotient of volume divided by flux, okay? The flux here that is driving the feed to the reactor is constant. So what's happening is now we're generating carbon dioxide. Now we're generating, so we have reaction A reacts to the product plus carbon dioxide. Yeah? What is our challenge? The carbon dioxide generates gas bubbles in the reactor because it is degassing, because we said the product has a concentration of 2 molar. Yeah, if you remember. Shortly switching back to transparencies. So we said this is the reactor we're destroying, and we said carbon dioxide occurs stoichiometrically. We produce 50 liter carbon dioxide per liter of reaction medium with 2 molar of our aspartate of this compound being added. So we generate 2 molar of carbon dioxide relates to 50 liters. Okay. Now back to the transparencies, to our whiteboard. Oh, come on. Yeah. So meaning, if we produce gas, switching with the colors. If carbon dioxide gas being produced, in consequence, reaction volume V is reduced because the liquid volume, so this is the liquid volume, is consumed by gas phase. Okay. So now we're in a situation that the flux here is constant because our pump is set to a specific rate. It is feeding the liquid phase. The reaction volume is a problem because that is reduced because of the carbon dioxide gas reducing the liquid volume. So if we're reducing, getting this term, the volume smaller at equal constant, so we get a smaller fraction, and in terms residence times will be shortened. So therefore, next step is, in a bad sense, residence time is shortened. If residence time is shortened, the consequence is, because we're in a plug flow reactor, remember the principles what Fernando also mentioned. Principle, plug flow reactor to contrast to CSTR, but end term is conversion is lower because we have less time to react. And now, so that's the starting scenario, okay? And now if we plot conversion as function of time, ideally, under no deactivation of the immobilized catalyst, anything we would expect, if we don't change the residence time at one residence time, yeah, so that would be the ideal situation. And ideal would be tau and V equals constant, because the flux is also constant. Yeah. Now, if during the course of the reaction we are generating carbon dioxide, as said, we're reducing this volume. Since we're reducing this volume, also residence time will be shortened. If residence time is shortened, the conversion will drop. And so, since we're in a continuous flow system, this gas bubble being here will also pass out. Yeah, and this one, and also this one by time. So we will get an inconstant situation with some more or less gas bubbles because they also agglomerate. It's not only individual small ones that would always be leaving. And in consequence, if we're looking at a realistic case, we would rather see something like this: gas bubble leaving, gas bubbles generating, leaving. So unsteady conversion. So this is CO2 generation in reactor, which is then true for what we just discussed down here. Okay, Now, what is the solution? The solution to this, that was Fernando introduced to you and what you see on the flow scheme. We put on the system an overpressure. And this overpressure, in the most simple way, we can use by integrating a valve in the outlet, generating some pressure drop, moving, oh sorry, this was the wrong one. Should be my laser pointer. By pumping in this direction, yeah. Or the second alternative is what we've seen in the transparencies, where here an extra overpressure is pressed on the reactor. Yeah. I hope it is clear now.
Yes, sir. Thank you.
Okay, perfect. Yeah, then let's continue with the repetition. So it's absolutely right. If you haven't understood something, feel free, just interrupt me. So then we talked about the degradation pathways of nitriles. Nitriles are these C triple bond N functions. Maybe I quickly, because we don't have it here, also once again draw it here for you. So a nitrile is C 1, 2, 3 triple bond N. We have a free pair of electrons at the nitrogen because the fifth row of the periodic table, and the carbon has any wrist couple teeth. And this is now the question, what can we do with these reactions? We're in the ligase business, so we always have 1 to 2, 2 to 1. Okay, back to transparencies. Now, if we apply an EC3 enzyme, a hydrolase, not a ligase, we would add water. Adding water will end up with the free acid and ammonia being released. And it's a hydrolase once again because we have 1, 2 starting materials generating 1, 2 products. Don't be irritated that we have here a number of 2 stoichiometrically for the water. If we're counting starting materials and products, we're just looking on the different kind of molecules reacting, not the stoichiometry if it's 1, 2, 3, or whatever the ratio of these individual ones is, because that is determined by the reaction mechanism and the kinetics, what we're not caring for right here at the moment. What you see in here in the degradation pathways of the nitrile, so the enzyme class 4 is a nitrile hydratase. The nitrile hydratase. So we have the nitrile, we're just adding 1 water, and since we're adding 1 water, we're ending up with the amide function, what you see here. Up here with the hydrolase, we have the acid. So in the end, with the nitrile hydratase, we're just adding 1 water molecule. We have 2 starting materials, 1 product. That's the EC4. And then we for sure can couple it with a hydrolase enzyme, what is an amidase, that is accepting the amide, adding 1 water, 1, 2 starting materials, hydrolyzing with the water the amide, releasing ammonia, 1, 2 products. Okay, that's the difference between those 2 pathways. Yeah, this is applied large scale, nitrile hydratase. So we see this with aromatic systems like nicotinamide, with the vitamin B3, what you have as food additives, or if you're more sportler, then you can even eat it that way. If it tells you a different story. Or in polymer chemistry, that's a very famous old process being established by Nitto-Chemical Industries in Japan. A lot of other companies do it nowadays, and BASF has just built a plant a couple of years back for this type, is to add water to this nitrile, and this is acrylonitrile, and the product is this one, acrylamide. Why is this such an important chemical? Because it's a bulk chemical being used for polymer synthesis. So polyacrylamide is if we do the polymerization of this, and if you're sitting in a car, for example, the cockpit, the plastic that's up there, that's normally polyacrylamide. So it's a bulk chemical. So there, these reactions are being applied. The big challenge is to make sure that this is not hydrolyzed, because we use water, as you see, and to stop the reaction in the right manner, that's not happening, what's shown here. But as long as we don't have a second enzyme present, as long as we are not in a under reaction conditions of extreme pH, highly alkaline or highly acidic, then we don't see the product degeneration. Yeah, and then Fernando introduced you different decarboxylases. Someone already asked, and these are part of a lot of cells. And the decarboxylase, as the name says, is splitting of carbon dioxide, or one can, yeah, maybe sticking to this for a moment, pyruvate decarboxylase. Switching over to the whiteboard. No. Okay. Okay. There it is. So pyruvate decarboxylase. Pyruvate, by the way, in German it's Brennstraubensäure. That is this compound. That is pyruvate, so it's a keto acid. And by the way, where you got to know it is in the section where we talked about transaminases, because a typical acceptor for amines in the case of transaminases, so enzyme class 2 transferases. Yeah, and pyruvate decarboxylase, which is abbreviated with PDC, catalyzes the split off of the carboxylic function, so that we're generating out of this acetaldehyde plus carbon dioxide. And let's see where the name comes from. And carbon dioxide. Therefore, it's pyruvate and decarboxylase. That's a function in a cell. Moving back to our transparencies. Okay, and that in the end is what's going on in the yeast. The yeast is using molasses and pyruvate contain generating this acetaldehyde, number one. But the enzyme does have a second function, as most of the decarboxylases. It can also be used for synthesis, and it needs not to be a carbon dioxide. It can also be a second aldehyde, what you see. So we see acetaldehyde reacting here with benzaldehyde, and this in the chiral manner that we're getting the phenylacetylcarbinol as an immediate precursor for ephedrine. And this was established by Krebs Biochemical. In Germany, it was a Knoll, that's an Indian company. In Germany, it's Knoll, formerly or being part of BASF, but BASF has now sold this business to a different company, forgot the name, who they sold to. And you can see also large volume, 30,000 liter batch. That's for the Indian company. For the BASF, it was not published, and for the new company, so 30,000 liter, 120 tons per year, 6 gram yeast cells for the whole cell system here per kilogram of this product. Yeah.
I had a question. Like, I did not understand the second part of this reaction. Like, how are the two compounds attaching in this manner here?
You mean so the acetaldehyde and benzaldehyde to this
Yes.
product? Yeah, there's a huge reaction mechanism behind this. And because the repetition, and we didn't, I think Fernando also did not discuss this last time. because it's a very detailed mechanism, but I can show you. One moment. Answer your question. So the PDC, the pyruvate decarboxylase, is connecting glycolysis and citrate cycle. And you need cofactors to move this. And in the cell, there is, in the end, in the first step, carbon dioxide being split. And then there is intermediate being formed, or two intermediates, and this is then stabilized with coenzyme A that is then fed to the citrate cycle for further conversion. And see, second. Yeah, I don't have the second question. Trying to see in here to show you. Here it is. This was one that's coming up. So if we're splitting this example of benzyl formate decarboxylase, the only difference is pyruvate just have a methyl function here in this position, and the benzyl formate decarboxylase has an aromatic function, benzol, therefore benzyl, or in English benzene, as residue here. Now, how this splitting is function if you do it in vitro or in a reactor, or if we're adding a second aldehyde, what you see here, so two aldehydes being combined, that is running with a cofactor, thiamine diphosphate. So that's answering your question. That's what I'm saying now. But this you do not need to know for the examination. Right? So I'm just answering because you asked me, but we're not asking you to do this in the examination. And this cofactor thiamine diphosphate is different to the cofactor nicotinamide, NADH, what we discussed about oxidase. It just needs to be present. It's bound in the active site of the enzyme. You don't need to care for recyclization. It is there, and during the catalytic cycle, it will be automatically recycled without any care from the outside. Why is this functioning? Not to give you too many details on of chemistry, but the aldehyde function of the donor, which is the benzaldehyde here in the middle, is attaching to this heterocycle you see in the middle, and it's forming intermediate thiazole, chemically named, and is covalently bound to here. And then the acetaldehyde comes in and is splitting this off as a product from this intermediate. That's how in principle it functions, but you don't need to know this in detail. But that would be the answer to your question. Is that okay?
Oh, yes, thank you.
So, yeah, so the thing what you should know, you need a cofactor, that's thiamine diphosphate or THDP, but you don't need to draw this cofactor, you just need to know for this lyase you often need cofactors like this thiamine diphosphate, but you don't need to care for any recyclization, what we have with oxidotases or anything else, it just needs to be present, that's it. Yeah, and by the way, industrially, you could start up with this pyruvate derivatives or the benzyl formate, but if you want to produce this industrially, you're starting up with the benzaldehyde. If you're using the pyruvate decarboxylase, then you could also, this would be a change. Then you would have here the pyruvate and the benzaldehyde being added here at this position. Why don't you start up with this beforehand by decarboxylation? The reason is easy. If you want to buy this on the world market, the pyruvate or the pyruvate derivatives, the benzyl formate, is much more expensive than the benzaldehyde or acetaldehyde. Therefore, from an economic point of view for your process, you're always starting up with, in this direction with the benzaldehyde and acetaldehyde because your starting materials are much cheaper, and you're sparing out one additional step. So now comes a short section about something new. What Fernando skipped because of time last time, I will quickly introduce. This compounds now information where I just want to demonstrate to you that you need to have interdisciplinary understanding between chemistry, biology, and engineering. Now, these compounds itself are, you can do this, but are unattractive. For an industrial application or pharma application, it's always good if you have any residues introduced, so any rest bound to the cycle. And typical ones are methoxy, H is the unsaturated, so the normal, and no substituent being added, or chlorine or nitrile residue. And now you're already triggered, you know if there's a nitrile, you can already do some other chemistry with the nitrilases, so nitrile hydratases, you remember? So chemically, you're more broad, but you can do in synthesis of pharma compounds. Now, the strange thing is, if you're looking at the enzyme and the production of the EE enantiomeric excess at this chiral center, you will see, depending on what residue you're putting into the system, you're getting different results. Nitrile even really bad. It doesn't seem to have really something to do with size, because methoxy is pretty big in comparison to just a proton, and you see it's almost the same EE in contrast to the other. So there must be a reason why this might be the case. And this we can do with physical chemistry. So physical chemistry we can use to describe what's going on here, and that I would like to demonstrate to you. What you see now has nothing to do with any biocatalysis. This is just classical physical chemistry. What we're looking at? We're looking at this reaction up here. That's benzoic acid. And benzoic acid with water. In water is dissociation. Any acid is an acid because it dissociates the proton. So that we have the dissociated acid and H3O plus as being a result. And this reaction, water is just taking place without any catalyst, and it's an equilibrium reaction, so where we have an equilibrium position at a rate of dissociation. Now, so that's given point 1. Given point 2, second reaction. Let's assume we do not apply the free acid, we apply an ester. So what you see here is the ethyl ester, C2 compound being added to here, so ethanol being added. This you could generate with glycans, for example, or hydrolase. And then we're taking a look at, if you're in an alkaline medium, how fast is this hydrolyzed to the free ethanol, alcohol, plus the free benzoic acid. So this is what we see in this plot, not considering the curve, we're coming to this in a moment. So here's plotted the logarithmic ratio of the formation of the reaction rate in terms of always comparing R with hydrogen, so unsubstituted case, to any substituent we see here listed, or that was here in the list. Okay, so always the ratio of unsubstituted to any kind of residue. That's for one in terms of the rate, and then in terms of the reaction equilibrium K, depending on the substituent. So the Hammett equation, what is this one, is correlating acid dissociation constant, so the equilibrium constant of the acid dissociation, with the rates of alkaline hydrolysis, the second one of benzoic acid. And it's always giving the ratio of substituted case to unsubstituted case, just a proton. And now the interesting thing is that we see that we have a clear linear correlation, linear because there's a logarithmic, double logarithmic plot here, and we can see we have a linear correlation. So if we know that it's given, you know, with this enzyme we're studying here, I might get this point here, you can already judge by physical-chemical knowledge where you will end up with other substituents. Now back to our reaction here. So this was the real data with our enzyme now, and we want to take a look how we can understand this. How can we explain this? You hopefully understood Hammett equation. Now for our reaction with the substituent, this looks a bit different. So we now take a look at the EE, not the rate. So we look at the rate, logarithmic ratio for this analysis of the concentration of the S to the R enantiomer that is being produced in the product. Okay, because that's our chiral compound being formed with the decarboxylation. So if the E is not 100%, then we do a specific ratio S to R, and because of the Hammett analysis, we have the logarithmic ratio S to R. And this is plotted as function of the substituent parameters, the sigma constant, and para means the residue is opposite to the other function. And so the sigma here is this parameter dissociation of the benzoic acid for this residue in daughter that we are focusing on. Yeah, and so once again, also for the biotransformation, we can see there's a clear correlation between EE expressed as logarithmic ratio of S to R and sigma parameter. And this is because the substituent we're adding here, and this is now deep chemistry, can either pull out electrons or push electrons to the system, and by this activating our starting material. Now, if we don't have the substituent in the reactant here in the para position opposite, but we put it in another position, either here or here, we name this meta position. It's also meta para, so that was para and this is meta position. And now, if with the same compounds, we do the same reaction with the same enzyme, and you take a look at this Hammett analysis, physical chemistry, nothing to do with biotransformation, you will see that someone shooting on a dartboard without hitting any goal. So broad diffraction. You would mean so. But that's not true. Take a closer look what is plotted here. If you're looking at this row, hydroxy, methoxy, so OCH3, atoxy, O, CH2, CH3, O isopropoxy, so it's OH, 1 carbon, 2 carbon, 3 carbons. Size increase. We're looking at this row here, we have fluorine, chlorine, bromine. That's also atomic radio. Size increase. Oops. Same as here. So here we can judge now, if we take a look at this, that just by observation of this radio, and you see it plotted in the structure drawing once again, that if we're in this position, we have a steric demand, so size determines reactivity and selectivity. So now by these studies we learn in the meta position, the steric, the size is governing, and if we're in the para position, so opposite here, then electronic parameters, Hammett constant, is governing. And like this we described in para with the Hammett correlation, in the meta position, we can describe this also with a term, and this term is the molar reflectivity or molar reflection. One can calculate this for any residue by taking the molecular weight divided by the density times the refraction, so refraction in light, with this term. And if you see, if we calculate the molar refraction for the individual compounds, these rows, what you see here in size, at the same sigma parameter. Same sigma parameter means same electronic effects. You can see once again we have a clear correlation. And this is technology that's being used nowadays. So digitalization is an important point, machine learning, AI, artificial intelligence. So these principles are being used by machine learning, artificial intelligence to understand what is going on in enzyme catalysis nowadays. Okay, I just wanted to add to this to you for some additional information, understanding how catalysis runs. However, these 2 points you don't need to know for the examination, please. But I hope you learned what interdisciplinary research means and how this interdisciplinary knowledge helps you to design the best process. Because let's say your partner from chemical synthesis where you are delivering your intermediate is flexible if you use an ethyl function or isopropyl function. Or maybe he might be flexible if you're using an alcohol residue here in the para position or chlorine. Then you can fine-tune the performance and the outcome of the reaction with the same enzyme without any enzyme optimization and without switching the overall process. Okay, yeah, then this was new part we inserted, and now we're finalizing a repetition from last time. We talked about hydroxynitrile aces, so enzymes that add HCN to an aldehyde, for example, which in nature is being found the other way, so it's splitting off CN, or for example, mandronitrile. And this is a highly toxic component, and it's for plant defense. And by the way, this is one of the reasons that babies should not eat, in English, mandrin. We don't want that. Just
Almonds.
Almonds, yeah, thank you very much, almonds. That babies should not eat a high number of almonds because the amount of HCN that is freed up is hard to be coped on with the small body of a baby in contrast to an adult person like us. So therefore, with babies, you have to watch out to eat almonds because of the HCN that's being formed and counting for the body weight. No? Come on. Yeah, and so in chemical industry, it's used the reverse manner. So we're starting up from the benzaldehyde, adding HCN, and then producing cyanohydrins. So this is what is called the hydroxynitrile component. Once again, you can define a specific stereocenter. And by the way, historically, this was the first asymmetric biochemical reaction ever described in a chemical lab, leading to a chiral compound in 1908 by Rosenthaler. Yeah, and this is being used large scale. So depending where you take the oxynitrilases from, might it be from sorghum, from manihot, from Hevea brasiliensis or prunus, they have different enzymes which are RS selective. So depending on the strain, you can select what selectivity you want to have for your enzyme, and then you can apply it large scale in processes. This, for example, is running by DSM in the Netherlands, or the production is, as far as I know, in Switzerland. But this is one way how to produce these chemicals. This we skipped. Yeah, then you briefly talked about isomerases. Isomerases, there we have one starting material, one product, and we're just switching chirality or any functional group. One example you can see here. So on the top line, E1, that is formerly an amide function that you see here with a racemic amine residue. Amide with a chiral racemic amine. So racemic pointing in our direction and backward, this is 1-to-1. And now the enzyme from enzyme class 3 with water is splitting the amide and just one enantiomer. That's the result what you see here. So in other terms, what's drawn up here is a kinetic resolution. It's a 2-to-2 reaction. And the enzyme is just cleaving one enantiomer. And you see it then consequent if you split an amide, just a cyclic one, but we have discussed this before. We end up with a free amine and the free acid, and then the L enantiomer is opened up, and the D is not reacting. Disadvantage: kinetic resolution, 50% yield of our target, but 50% left over. And this is now where the isomerases come into play. Namely, they are under the right isomerase, they are racemases, where the name you can already judge, catalyzing racemization. And so if you combine now with this kinetic resolution up here, racemase, that's E2, enzyme class 5, we have one enantiomer, but this enzyme, without any further help, is racemizing to racemate. So one enantiomer to 1 ratio once again. And now we're moving into again, we have once again more we can split here. So in the first place we get 50%, we have 50 left over. If this 50% we're splitting, we're re-racemizing 1 to 1, we have 25 in the next round to cleave overall, ending up with 75%. And the more rounds we run with racemase, the more pure product we get. Toray Industry in Japan is running this at 4,000 ton per year scale. Oops. And there should be a second. I'm showing you in a sec. One moment. Yeah, and this is similar process scaled by Evonik, former times Segusa, nowadays Evonik, where they also won the Frost and Sullivan Award, where we have hydrogenase. It's like an amidase, just splitting such a cyclic compound, and by integrating racemase, by selecting L or D, forming the D or L product, and the racemase one produce selectively one or the other. You don't need to know by heart. Not for the examination, but their industrial applications, should it be? Yeah, with this, we're at the end of repetition from last time with more details to be added. Any questions to this point? I don't see any. Then I would switch over to the whiteboard and now do with you one for the residual time. We have one exercise, what in terms what you could also be tasked for the examination. And this kind of for sure will be one task in this direction. And so let me switch to the whiteboard. You will see in a moment. Here it comes. Okay. So the task is the following, like what we talked before. We have one target compound, and this target compound now will be an amine. And this is this compound here. So it's an aromatic amine. And now the task is that you should think about different reactions from different enzyme classes, making use of to synthesize this compound. And you should always name substrates, so all starting materials, all products there are, not name in terms of a word, but to draw it like we're doing in a second. And you should name the enzyme class. Enzyme class, EC. So you asked me what are typical errors where people have problems in the examination. This is one point, namely to think of all the products and all the starting materials you need if you draw something now. And so to start up with this, does anyone has a suggestion where we should start up? How we could do this? To synthesize this chiral compound?
Maybe use transferase.
Sorry, louder.
Transferase.
transferase. Yeah, okay, perfect. Let's start with this one. Good suggestion. So the first example we're talking about is transferase. And transferase, as we know, is an EC enzyme class 2 version here. And specifically, what we're using here is a transaminase. So we have two ways how we can run this. Now you should, in the examination, often is asked named from 3 different enzyme classes, 1 reactions. You can run with the transaminase different reactions, and it's okay if you just pick one, but that's up to you. So, but I will now draw all alternatives, and we will continue next lecture, so that you get an overview once again. So, possibility for transaminases 1.1, that would be that we would start up from the ketone acetophenone. If I name these names, you don't need to know. You need to be able to draw the structures. Then we need to have an amino donor. So there, for example, we could use isopropylamine, or now I'm just drawing here alanine. These we discussed in this lecture on transferases, transaminases. So this would be alanine, for example. You don't need to write the English name in words. Then for sure we will use the transaminase, or EC4 you can draw on top of the line. And then we're generating this product. So this product in that chirality. So therefore, we are now drawing our product, and we're happy that we can produce it. And now watch out. That's often an error, a failure in the written examination, because in the task it says you should give, in the written task, all products. Sure, you make this product, but you still have the alanine with the donor, so you have a side product that you need to give, because for the process design industry you need to be aware of all chemicals you are consuming, generating. So therefore, what you still have to write down here is a side product, which is pyruvate, that is being generated. And so we do have here a ketone, and the ketone is being reacting with the amine that's being transferred, and the amine is generated in our product, namely to the ketone function, and this ketone is still left over what we have in the what we have in the byproduct, so to say. Okay, this would be now sufficient for the answer. Okay, so the question was name our substrates, our products, and the enzyme classes. These are the sorry, you don't see my mouse here. So substrates were asked, products were asked, enzyme class were asked. Enzyme class was given 1, 2 substrates, 1, 2 products, enzyme. More is not given. Now I will additionally use these examples we're going through today and next time for a repetition of different stuff we have learned in principles in the lecture. Therefore, question to you right now, I don't have a many video for this because it's discussion going on. What is the chirality of this product? Is this S or it is R? Who would like to answer?
The first one is S.
Yep, perfect. So this one is S, and just for repetition, so the hydrogen not drawn would go here to the back. So we don't draw it. Heteroatom has our highest priority, so this is 1. then we have this or this left over, but the aromatic ring has more carbons to it. So this being 1, this being 2, this being 3, and so we have a left turn, and so it's S. Okay. So next question. Someone else to answer. What is the expected yield you have in this reaction under ideal conditions?
I would say 100%.
Right.
Yeah, 100%.
Absolutely right. So yield is 100%. Namely, we have one starting material, and we're calculating its yield in terms of our product generated from this starting material. We can transform 100% over here in ideal manner, because this is our Carl function. And since this is the case,
I have a question to that.
Yeah.
We would definitely have, or it would not be possible to have anything in ideal conditions less than 100%, because would it also not consider the side product that we have with the pyruvate? Could that not also react with the transaminase?
Yeah, good question. Thank you for asking. I'm answering in a moment. Let me continue one moment. Yeah, I'm coming back to your question. So we just found out, ideally we have 100%, and therefore, just to complete this, we name this an aromatic synthesis, since it's no canonical solution. Okay. Now back to your question. You asked why don't we have a backward reaction? Yeah. That was a question. Why does not the pyruvate? So why not this takes place with this reacting in this direction? Yeah. And that might be, yeah. And that's good that you're asking this, because now you have learned that we have reversible reaction systems, and now it depends on the substrate structure. So do we have here residue involved? Or do we have a residue here and here? Defining the specific equilibrium in such a reaction. So it might not be 100%. There might be some backward reactions. The overall equilibrium, let's say, might be by 95 or so, depending on the substrate structure. So the question's right, and you need to consider this. But in principle, under ideal conditions, we would see the 100% in a realistic manner. Ryan's question is absolutely right. It might be that we have something like 95 or 90% conversion, and then we would need to think about in situ product removal, so either removing the amine or the side product. So all these technologies we have discussed in view of in situ byproduct removal. One possibility, if Ryan is right, to shift the equilibrium was what we discussed in a total different manner. That was the observed cases to shift the equilibrium, doing stripping. So we did this with substrate coupled cofactor regeneration, because we could alternatively different color. Alternatively, we could apply here isopropylamine, and the byproduct being generated out of this would be then acetone, because we are getting rid of the amino function and we're generating this keto function. And now, if you remember, that's what I mean with learning principles. If you remember substrate coupled cofactor regeneration, where we had this problem that we are thermodynamically limited in substrate coupled cofactor regeneration, we had the same situation where we're ending up with acetone. But there we started from the isopropanol, and here's isopropylamine. It's the amino function. But this one we learned has a low boiling point, and within a bubble column or under vacuum, we can strip out, release, or separate the low boiling component acetone, which was then the solution to let this system run to shift the equilibrium. So answer to Ryan's question is, if it's not good enough, I switch idly over to isopropanol as the amino donor instead of the alanine, and then I get a side product that I can more easily separate. Okay? Good. I don't see any comments.
If we would have a different side product in the first reaction, so if the pyruvate would, for example, be the acetone,
Right.
would we not have so much of a back reaction because the enzyme would not recognize our product?
No, the enzyme. So what I was talking about now is that as starting material we use the alanine here instead of the pyruvate. Yeah. So replacing this. The byproduct we are generating is not the pyruvate. It will be the isopropanol. Both, for sure, they will differentiate in the Km values for the backward reaction. Okay, so your comment or question is right. But the trick that we would be applying is that we're going to separate this separation via in situ product removal. ISPR, in situ product removal, we discussed this before, so that we blow in gas, and with the dry gas we strip out the acetone, low boiling point, distributing gas phase, or that we have a vessel where you put a vacuum on top and by this remove the acetone. Is this clear now?
Yes, thank you. But the backwards reaction for the pyruvate would still be more likely than for the acetone, correct?
Yeah, correct.
Okay,
but
thank you.
It's not that big of a difference, so it's rather the big difference is that the acetone I can easier separate than the pyruvate.
I understand. Thank you.
You're welcome. Okay. We have still 5 minutes, so let's finalize transaminase. So we have a second reaction we could run with the transaminase, and this points in the direction what Ryan was asking just before. So we named this 1.2. And that in the end is the backward reaction, namely that we're in here starting up with a racemic amine. And to denote that it's racemic, if you remember, we always draw a dashed line. NH2, just adding to this racemic. And we are reacting this now for completeness here with the, let's say once again, but now with the pyruvate, because we need an acceptor. Pyruvate. And this would now be kinetic resolution, we would name it, because we're starting up with a racemic component we are splitting. And once again, we need the transaminase, TA. And our product will now be the non-reacted leftover enantiomer. Remember our discussion, we discussed this in detail in the case of the hydrolases. So our product is the unreacted leftover enantiomer, plus we're getting out of the pyruvate the alanine, a side product. Plus, where we have moved away the amine function to the alanine over this one, we get now the reaction product itself. And the reaction product itself is the acetone. phenylacetone. So here we are in the situation with a transaminase and splitting that we have one racemic starting material and second acceptor of the amino function. We're generating one reaction product, namely the away transported amine function. We're generating a second product out of the pyruvate, and we have our target, which is the leftover non-reacted from the racemate. Once again, our product is S. Now, not part of this examination question on such examples what we're discussing, but other question could be, what is the non-specificity of the enzyme that I do need to run the reaction? Oh, that's nice. Let's see, it's hard to read. I will upload these transparencies after, so by tomorrow, okay? So the question is, what is the non-specificity of the enzyme we're applying here for this reaction?
I think because we have S that is untouched, then we are going to apply the R so that we can get the R word.
Right, that would be now the absolute 100-point answer. Here we need an R transaminase because the S is untouched. Out of the racemic resolution, the R is reacting to the acetophenol. Okay, absolutely right. What would be in the case of the enzymatic synthesis, the transaminase? Would that be S or an R?
It would be S, of course.
Absolutely, because there our reaction product is the S product. That's nice. Okay. Yeah, with this, it's 43. We're at the end of today's lecture. Next time, we're continuing repetition, and we will continue with this overall task. However, we will use this also to repeat a little bit on kinetic resolution, EE conversion plots, and this stuff, so that you have an overall repetition by the end of last lecture. If any questions coming up to your mind, collect them, either post them tomorrow or then next week, and I'm happy to answer it. Thank you for joining my lecture. Stay healthy, and see you tomorrow morning again at 8 o'clock. Bye-bye.
Bye-bye.
Bye.
Recording stopped.